Hello, and welcome to lesson 22 of this Introduction to Probability of Wolfram. The topic for this lesson is joint distributions. Let's begin. So far, there was no easy way to create a distribution of 3 dimensions or higher. Ideally, you would want to join multiple univariate distributions in order to make a more complex multivariate distribution. You'll see examples using functions to join and to separate probability distributions. Experiments often have multiple measurements. These may be analyzed separately or together as multiple independent univariate distributions joined. This is called the joint distribution, or product distribution in the Wolfram language. It's used to answer questions based on multiple distributions simultaneously. Okay, let's take an example, a simple one, with 2 discrete distributions, one joined to the other. You throw 2 dice. What's the probability their sum is a given number? Each die is uniformly distributed over all 6 values, so you'll need to use the discrete uniform distribution. So, to get the probability of the sum of x and y being a given unknown, where x and y are the product distribution of the discrete uniform distributions. Since values go from 2 to 12, you can plot it from 2 to 12. This can easily be extended to any number of dice. For example, 3 dice plotted here. Let's try a fully continuous situation. You and your love interest are trying to meet at a certain place between 5 and 5:30 p.m. You both arrive uniformly in that interval independently and stay for 5 minutes. What's the probability you meet? Each of you represent an independent uniform distribution, so that can be formulated as the product distribution of 2 uniform distributions. Then just calculate the probability of the absolute difference being less than or equal to 5 minutes, and you'll get 11/36. You can visualize the success region using region plot on this situation. Now, what if you want to join discrete and continuous distributions? Here's an example. A waiter's weekly income is based on work hours and tip. The work hours are binomially distributed like this, and tips are gamma distributed like that. If the waiter is paid $13 hourly, then what's the probability the waiter earns more than $550 the next week? Just form the product distribution for the income, then find the probability 13 times the number of hours plus the tip is greater than 550 over the income. So now you know how to make multivariates from simple univariate distributions. But what about the inverse? Can you extract a univariate distribution back out from a multivariate distribution? That's quite easy actually, and it's called the marginal distribution. You just input the multivariate distribution and the dimension you want to isolate, and there you go. For example, the first marginal distribution of a product of 2 Poisson distributions is quite obviously a Poisson distribution. A somewhat underwhelming example. So let's take another one. A string of a length of 1 is cut according to a 15-10-5 Dirichlet distribution. What's the expected proportion of the first part of the rope? I'll assume you're not familiar with this distribution, so let me explain a bit. based on the plotting of the marginal distributions. The Dirichlet distribution attempts to have three pieces of relative proportions of 15, 10, and 5. So the first cut must be around 1/2, and the second cut around 1/3. As you can see from the mean. So now you can go from many univariate distributions to a joint distribution and vice versa. Are we done? Well, that's all assuming independence. You may have already realized that some univariate distributions are linked together in more complicated ways, like with the covariance that we saw in the multinormal. The copula distribution is just that, the characterization of independence between univariate distributions. The copula is one of the most powerful tools of all probability theory. Mathematically, any multivariate distribution can be modeled with a set of univariate distributions and a copula, together called a copula distribution. Practically, however, this implies the implementation of every possible copula, which is not really realistic computationally. Anyhow, this powerful tool has applications in finance, engineering, data analysis, medicine, climate research, and signal processing. The copula distribution is a generalization of the product distribution, and that's easy to prove. For example, joining two independent normal distributions can be done in two ways. The copula distribution of these distributions on the product option, or simply the product distribution. Computing the PDF will bear the same results. So what is this dependence magic called? The kernel, also called the copula, but never copula distribution, is the type of relationship between univariate distributions. If you want more information, you can consult the documentation of this function. But just to show you how diversified and interesting those relationships are, I'll apply most kernels on two simple uniform distributions. And the result speaks for itself. And what about the marginals, those univariate distributions? What happens when you vary them? Notice that you can use both discrete and continuous univariates, but I'll stick to the continuous for visualization. Well, most applications of copulas actually only require uniform and normal distributions. I must warn you, copula distributions easily get incredibly complex. But for the sake of beauty, let's try many different marginals with a standard normal distribution and the Frank kernel, just for fun. And yeah, the variations don't disappoint. Okay, finally time for an example. 2008's global financial crisis can be partially attributed to the misuse of the Gaussian copula distribution. This corresponds to the binormal or multinormal kernels in the documentation of the copula distribution. But how is that possible? Well, let's learn some investment terms. A bond obligation is a univariate distribution with a 0 for immediate default and a 1 for complete payment. So the true value of a bond obligation is somewhere between 0 and 1. You can use a uniform distribution for that, or really any distribution with a domain of 0 to 1. A CDO, without getting into details, is simply a package of bonds. You can empirically relate bonds together using correlation and covariance. So here, we're going to build a CDO and use the binormal kernel to form the distribution. What is the probability the sum of these bonds is more than 8? Take the probability of the bonds sum to more than 8 as distributed in the CDO. Notice the variance of the bonds is determined from data. In periods of quick change, copula distributions are hard to maintain and don't update fast enough. So in 2008, the Gaussian copula was still a new concept to the market, which led to it being misused in the context of insufficient data at the extremes. To summarize, the joint distribution or product distribution combines independent univariate distributions. These can be extracted using the marginal distribution. However, joint probability is not the only way to combine univariate distributions. Using copula and univariate distributions, the copula distribution can generate any multivariate distribution. But what are the limits of this random variable algebra? Many crucial probability theorems are part of asymptotic probability, which will be seen in the next lessons.